Now let's cross our fingers. So back to the notes. What you would see at the top here is the idea that if I ask you to integrate a vector, so R of t is a pretty common notation if you haven't noticed, indicate that we're dealing with a vector. R of t gives us both an x position and a y position. All we're doing is splitting these up into two separate integrals. One for the integration of the f function, and then the other one for the integration of the g of t function. So for number one, that's all we're really doing. So you're going to split this up. You're going to go 0 to pi for the cosine of t, and then whatever this will give us will be our I. And then we're going to, you can do what you want with the minus sign. I'm going to leave it as a minus. You could do plus and negative too, but I'm going to leave it as a minus. And we're going to go 0 to pi, integrating the 2t, like this, dt as our j. Then just two simple little problems in one. So we're going to do the antiderivative of this. That's the sine of t from 0 to pi. Plug in your upper limit minus the lower limit. The y coordinate at pi is 0. The x coordinate at pi is 0. So we're going to get a 0i. If that's the case, you don't necessarily have to write the 0i. You could just leave that blank. But I'm going to leave that just so we know it's there. The next one, same process. You're going to do the antiderivative of 2t, which would be 2t squared divided by 2. So just t squared. And then plug in your upper limit, pi squared minus the lower limit of 0 squared. And then we would do minus pi squared j, and then that's our guy. That's our answer. And what I was saying is, if you just ever see, or if you ever write just the negative pi j, then it's implied then that I has a coefficient of 0, and that would be okay. All right. But I do like showing it, especially for the first one we've done, to know that that's just what that value ended up being. All right, number 2, 3 dimensions. That's a Calc 3 idea, but just to kind of hammer home sort of what this gets at, IJK, same process. We would want to split this into separate integrals, so 1 to 4. And I will not give you 3 dimensions tomorrow, so don't necessarily worry about this. But certainly the I and the J term, fair game for tomorrow. So let's split these up. And then 1 to 4, and then 1 over 2t. The 2 first ones are the big ones that I want to make sure we're squared away on. All of them are kind of important. This is our basic natural log. So I want you to understand, when we just have 1 over t to the first, this is definitely the natural log of t from 1 to 4 as our I. And then you're going to plug in the upper limit minus your lower limit. Natural log of 1 is going to be a 0. So we just get the natural log of 4 as our I term. The other 2 are also natural logs, but they're also ones that you want to be a little bit more careful of. As long as your t here has a coefficient of a positive 1, then we get this natural log. We don't get anything extra. If you look at this one, notice how this is a coefficient of a negative 1. So this goes back to when we kind of did those partial fractions. We want to do this without having to go through the u substitution process. You will still definitely get the natural log of 5 minus a t. But if we actually did u substitution, think about what u would have been. It would have been a 5 minus a t. Doesn't the derivative of that give us an extra negative 1 that we didn't originally have in that problem? So if you can recognize that, we can avoid this process and know that we then just have to divide by the negative 1 that t's coefficient would have been. Which then well, I'll write it in the next step. I want to leave it there, so if you reference this later, you kind of know where that came from. But ultimately, we can then put the negative in front of that natural log. That's what I'll do in the next step. So I'm going to now do plus, and then I'm going to do a negative natural log of 5 minus 4 minus the negative natural log. Getting a little congested here. Negative natural log of 5 minus 1. And again, this is our j. Forget that. This gives you the natural log of 1. Natural log of 5 minus 4 is going to be the natural log of 1. So that's going to go away. Here we do get plus the natural log of 4. That would be the only thing that we're left with for our j term. So it should just become the natural log of 4j. Then the way we want to handle this next one, this is also a natural log, but to make things a little bit nicer and easier, this really is our coefficient, right? We can always pull constants out. So let's pull the 1/2 out so that really all you are looking at is a 1/t. So we basically have turned it into the first one that we did. It's just you're going to have a coefficient of 1/2. So it's 1/2 the natural log of t from 1 to 4. And then whatever that gives us, that would be our k term. That would be our, once we get to that third dimension in your life. And then plug those in. So we get 1/2 natural log of 4 minus the natural log of a 1. That's our k. Certainly would take the 1/2 natural log of 4. Natural log of 1 again is going to be a 0. I'd take that, but the 1/2 could also become the power of a 4, which is the square root of 4. So you could also write this as the natural log of 2. Right, so this could become the natural log of 2 if we simplify that. All right, but just kind of, drives home the point. If we have 3 integrals, you're just splitting it up into 3. All right, we don't necessarily need to do all of these. Go to number 4. I kind of want to do number 4 just so you see one where our methods are different. So if I go to number 4, we definitely want to split these. So let me throw the integral from 0 to pi over 3 in front of the secant squared. We ran into this a little bit with those higher order trig substitutions that we did last chapter, but we have 2 very different methods to do this. The first one we know, right? Like we can do the antiderivative of secant squared. That's a known derivative of tangent. So we can jump right to tangent from 0 to pi over 3 as our j term. There should be a j there now that I look at it. I forgot to put that guy in there. And then we know we're going to plug in our upper limit minus our lower limit. Whatever that gives us is going to be our j position. Tangents make me think a little bit. I don't know about you. What's this? So this is 1/2 root 3 over 2. So this is our pi over 3 point. Tangent is the y coordinate divided by the x coordinate. So root 3 over 2 divided by 1 over 2 should just be a root 3. The tangent of 0 is 0. So then that should be our j term, just root 3j. The one that I skipped, though, we can't just do that antiderivative. That's not the one we can just look at and know. This is one that when we would have done this would require a little bit of u substitution. You could pick sine or cosine. They would actually both work. But sine-wise, I think letting it be sine of t works out nicer because then our du just gives us that positive cosine of t. So when we do our substitutions, the 2 would still be there. And then the sine of t is your u. And then the cosine of t and then the dt would be our du. Then we want to get our new limits. So here's how we convert them. U is the sine of whatever our angle is. So if our x or time was a 0 and I plug that in, the sine of 0 is 0. So that actually stays the same. Our upper limit was pi over 3, but if I plug that in, the y coordinate at pi over 3 I have over here, that's the root 3 over 2. And then we just want to now antiderivative, upper limit, lower limit, okay, all that fun stuff. So we do 2, antiderivative is u squared over 2 from 0 to root 3 over 2. The 2's then obviously cancel. Plug in your upper limit, so root 3 over 2 squared minus the 0 squared. Forgetting my I also, sorry. And what's that give us? 3/4. So we would get 3/4 I plus root 3j, and then that's pretty much it. Okay, so that's how we would handle a definite integral with these. We'll kind of show how what these would be useful for here in a minute with all these AP questions that you're going to have coming up. Whoa, what did I do there? Let's go back. All right, 3, if you want to do that at some point, if you're bored, feel free. We're going to move along, make sure we get through enough of those next couple pages. So now let's go to number 5. Let's say we don't have a definite integral. So this says the velocity of a particle is moving in space, and you're given the velocity vector. Find the particle's position as a function of time if So understand, this is our position vector and it's 2y. So underneath that, let's actually write a little bit more detail. Notice how there is no j. So what that implies is our coefficient for j is a 0. So if I give you 2i only, that means our j coefficient is a 0. So here's how we want to do this. First thing we technically want to do is multiply the dt over. So we're going to have cosine of t I minus the sine of t j, and then the dt gets multiplied over. It ends up being the coefficient of both. We'll say coefficient, but it's on the back end of it. Since this is our velocity, same process we would have thought before, and I'm asking you for a position. We're going to go from velocity to position. Then we need to then do the antiderivative of these. The antiderivative of 1 dr would give us r, which is good because that's our vector. Our position vector r of t would equal. Then you're going to do the antiderivative of this cosine. So that's a sine, and then that produces its own c. So that's the c for our horizontal position. We don't know what it is yet, but we know it would have that plus c. The next one, if I did the antiderivative of a negative sine, that would end up giving me a positive cosine of t, and then we get a c for that one as well. Now we need to figure out what our c's are. So understand what this expression here, combined with this expression here, what these two things are telling us. What this is really saying is at the time of 0, my x position is 2, because I corresponds to that position. So down here, what this really is, that's our x of t expression. So x of t is equivalent to the sine of t plus our constant, if we go from a vector into the kind of a parametric mode. So what we know is our x position is 2 when our time was 0. So that particular c is a 2. So when we now go to write our position vector in its entirety, we now know our x position is the sine of t plus 2. And then that is what we have as our I, or our x position. We do pretty much the same process then with our y of t. So this, since it's our j term, this is our y position at any time, and that is cosine of t plus our constant. Over here, what this was telling you is at the time of 0, since we have the 0 as the coefficient of j, that our y position at that time was a 0. So using that, we're going to let y be 0 at the time of 0. Cosine of 0 is a 1, so we're going to take that 1, subtract it over, and what we find is the c in our y term is a negative 1. So then we can do, and then our j term is now cosine of t, and then set a plus c, we do a minus a 1, and then that's our position function. We can now figure out our x and y position for any time that we want. So very much like everything we've been doing, it's really just two little problems in one. One for the x, one for the y. Right? All right, so same process here. So we'll knock out one of these again. I want you to see a couple of these so that we understand when you see this notation that at the time of 0, r is equal to I plus j. That's just a different way of now telling you at the time of 1, since I has a coefficient of 1, that's just telling us our x position is at 1 at the time of 0. Same with our j. Now our j does have a coefficient of 1, so that means at the time of 0, our y position was 1. That's our initial position at the beginning of this time. When we now separate these and do the antiderivative of these, r of t should equal, so we're going to do the antiderivative of our I term. So that would be t to the 4th over 4, and then 4t squared divided by 2 is 2t squared, and then that's the constant for our I term. And then we now have to do that with the j term. That one's super easy. That would be t squared over 2 plus its c, that's our j term. Oh, I'm getting off the screen for you guys in here. This over, there we go. All right, so same process now. The I is your x position. So really this expression right here, that is our x of t equation. To figure out that c, we want to use our x position. So what we have written over here to the side is that as long as we let our time be 0, so 0 plus c, then our x position was a 1. So we know that c is going to be a 1. So if I go to now write this, we would have the t to the 4th over a 4 plus a 2t squared, and we know that c is a 1. We now have our horizontal position for any time we want it. The j coefficient right here, the t squared plus c, that has to be our y position, our y of t. We know y is going to be a 1 at the time of 0 from this over here. So we do those substitutions, and we see that that c is also a 1. So then we would now write this as t squared over 2 plus 1. We can now get our y position anytime we want it. Okay. Hopefully feeling this isn't too bad. It's just more work. You know, you see one problem, but you're really doing two. But it's largely the same thing we've been doing. So that's the integration of vector. What I then did, so those taking the AP test, this is like 90% of the time one of your free response questions. So I just printed out a handful of these. There's a couple of elements of these that I want to make sure that you see that you need to be able to do tomorrow. So I think I have these. So go to this one. This would have been a non-calculator question. The next two, I believe, are calculator. This would have been non-calculus. So this is one that you wouldn't have the calculator in your hand. We should be able to work our way through all of this. Pretty simple little setup. They tell you that a particle has an x position of x of t, y of t. So they're telling you this is the idea of a parametric equation. Here's your initial position. At the time of 1, our x position is 2, our y position is 6. And then they tell you that your velocity vector. So notice in this case, when they wrote it, they didn't use IJ notation. They just wrote this as an ordered pair. They didn't even use the carets. They just used regular old parentheses. But since they're telling you this is a vector, this is our velocity vector. A, pretty straightforward. They make you deal with some negative exponents there, but we did this yesterday. If that's our velocity vector, same rules that we've dealt with all year. If I'm currently at my velocity and I want the acceleration, I just want the derivative of that expression. So the acceleration vector, so we can just write this as a of t with a little vector over it. Since they use parentheses, continue to use whatever format they used. So let's continue with these parentheses. Actually, you know what? I like writing the negatives first, so I'm going to stick to that because I just see too many people make mistakes. So let's write the velocity vector with negative exponents. You think you don't have to do that, feel free. Well, once they're with negative exponents, then this is pretty hard to mess up. So now our acceleration vector at any time would be a positive 2 t to a negative 3, and then a negative 2 t to a negative 3, which is then 2 over t cubed, negative 2 over t cubed. So that's our velocity vector at any time. They're asking you to evaluate this at 3. So you take your time of 3, plug that in, and we should get 3 cubed is 27. So both of those have that in your denominator. And those are 2 free points right there, all on our way to our 5s. Okay, so that should be nice and easy. B is what we just did. So that's kind of why I put this in this packet, because now we can answer all of these questions. They're now asking you to find the position. So it's the exact same thing we did on the previous 2 questions. So if I now write my velocity vector, part B, so here's our velocity vector. It was that 1. I'm still going to rewrite this with negative powers. So when we do our antiderivative, we don't make any careless sign errors. Do they tell us what to name this? Yeah, they don't tell us what to name this, so I would probably call this R of t. That's the generic, most common version of a position vector. So let's call this R of t. we're going to do the same thing we just did in the previous couple questions. We now want the antiderivative of these. So now we're adding 1 to this exponent, and that's what's a little tricky, is just the negative exponents. People tend to make little mistakes with that. And do the same thing with your y. So this would be 2t plus t to a -1 over -1 plus your constant. I would recommend rewriting that real quick before you start your substitutions. So we're going to get t plus 1 over t plus your constant. 2t minus 1 over t plus that constant. And then now we're ready to do your initial position and all that good stuff. This is your x position, the t plus 1 over t plus c. Let me write over here what they gave us at the top. At the time of 1, our position was 2, 6. So this is what we're now using. So if I say this is x of t, if I let my times be 1, I know my x position is 2. Okay, this doesn't happen very. Did we all get 0? Did I get 0? Yeah. Yeah, okay. Not very often you're going to get a c of 0, because if you forget your plus c, then you still get it right. But in this case, we do. So our position at that time would be t plus 1 over t, and then our c ends up being just a 0. So that's a comma there. We do the same thing with our y's. So now y of t is the 2t minus 1 over t plus c. We know our y position is 6. All right, that's right here at the time of 1. So let your time be 1, let your y be a 6. So we get 2 minus 1 plus c. So this c ends up being 5. So then our vertical position would be 2t minus 1 over t plus 5. All right. This is not ringing any bells to me. Are we all getting this? Okay. All right. Now, the answer to the question ultimately was at 3. So I'm just plugging in 3. Like I said, this would be non-calculator. So if you're scared of fractions, when you do this right here and just do 3 plus 1 over 3, that's a perfectly acceptable answer. And in fact, I would strongly recommend you just leave that. Why do more work? Why increase the opportunity to make a mistake? That's your answer. Now, multiple choice, you better be able to simplify it, but this was not. This is a non-calculator free response. Just leave it. If I plug in the next one, I'd get 6 minus 1 over 3 plus 5. If that really gets you worried, just leave it. And again, they're going to take that as all the points you could possibly get would be perfectly fine with that answer. Okay. All right. Numbers or letter C, set that one up. This one I want you to think about a little bit. A should have been pretty straightforward. B is what we just had done a couple problems of. Think C through and see if we could figure out a way to deal with that. Certainly something we've talked about in the last few days, but see if we can now kind of remember what we talked about with this. And remember, it's non-calculator for us to solve this also, once you have it set up. All right, your hint, everything you need to know is right here that I'm highlighting. Slope of 8 is what we're really focusing on. That should mean something to us. When we talked about slopes of parametrics, how did we find slopes of parametric curves? However we did that, you're just setting it equal to 8. We want to know, when does our slope equal 8? All right, let's see if we got this set up right. So slope is still, just like you learned in 6th grade, change in y over change in x. We've now, since we really don't want a change at all, we're dealing with that infinitely small kind of limit there. It's dy over dx equaling an 8. So if you recall, the way we found the slope with parametric equations, we had to do dy dt divided by dx dt. And then now in this case, we know that it must equal 8. So what I highlighted is slope equals 8. That's what you then set up. Both of these you're given, right? So these are what we were given at the beginning. Dy dt is the derivative of y. That's actually the equation that they gave us. Same with the dx dt. They gave us the dx dt. I'm going to try to save a little bit of room here. So dy dt, actually I have it in front of me here. Was 2 plus 1 over t squared. That was our dy dt. And then the dx dt was 1 over, or 1 minus 1 over t squared. That's what has to equal 8. No getting around this one. All right, this you do need to now go through the algebra to solve this, so this you can't freak out about. We got to be able to handle this. So I'm going to multiply this over, so we'll get the 2 plus 1 over t squared. I'm going to distribute the 8 while I do that, so we'll get 8 minus 8 over t squared. You can do some different things at this point. If you want to get rid of the t squareds from your denominator, multiply everything by t squared. I think that's actually a fairly solid thought. So that's what I'm going to do. Let's just get rid of the t squareds out of the denominator. So multiply everything by t squared. Because I think from there, most of us are probably good. Now we can go through and start to solve that for the t. We initially get plus or a minus whenever we do our square root. You're going to get a plus minus root 3/2. That's your answer, sort of. It's not quite our answer. The reason we're going to settle in on that positive one is because if we go back up, if you reread the problem, you were told right here that this is only defined for any time greater than 0. So that eliminates the possibility of the negative solution being an answer. And then that's our time. All right. D. This is pretty typical. The D is usually some little, not all the time, but very much the D is sort of like an abstracter idea, a little harder idea. Just try to set up D. This is not impossible. This is by no means crazy, but it's not a straightforward question like I think A and B were. C was a little bit harder. D now, see what you think. Oh, I ran out of room. Okay, so hopefully what you're thinking or what we're looking at, we're picking up on some keywords here. We want to figure out what slope does our line have as our time goes to infinity. So we can kind of just put those ideas together. All right, what is the slope as our time goes to infinity? What we're really looking for is the limit of dy over dx. Dy dx is our slope. We want to know what is the slope as time goes to infinity. Just like you set up in part C, we're going to do the dy dt expression over the dx dt expression. And then we're trying to figure out what that limit is going to be. Don't overthink it. Just because it's a part D doesn't mean it's supposed to be hard. It's usually just different. It's just not this straightforward standard little find the derivative question. Right now, what do you think that is? This is not a hard question. I promise when you see it, you're going to be like, oh yeah, that was not hard. All right, anybody confident in this answer? Got some thoughts here. Brian? It is 2. So Brian said, is it 2? The answer to that question is yes, it is 2. How'd you get that, Brian? Perfect. Couldn't have said it better myself. You didn't hear him at home. He said 1 over a really big number. So think about 1 over 1 billion squared. He said it's going to get smaller and smaller and smaller and smaller. Same thing happens right here, right? This is just going to become a 0. 2 and 1 are constants. The limit of any constant is that constant. So all we really end up with is 2 divided by 1. Our limit ends up being a 2. Okay? Good. All right, next one. A is the one I really wanted to make sure that you see here. This is a calculator question. So as you kind of read through this too, largely straightforward. Here is dx dt. dy dt, they're being very mysterious about. They're not going to give you the dy dt. And then at the time of 2, here's your initial position. So if I ask you for a velocity vector, we have some information here to give us, but we don't have this. All right, but part A, they want you to find the x coordinate of the position of the particle at the time of t equals 4. So here's why this is a calculator question, and here's why I wanted to make sure that we get to this. You're going to probably get one of these tomorrow. What we definitely have to do, if I want the x position, and this is the derivative of x, then we definitely need to be integrating this dx dt to figure out 3 plus, of course. So when we separate our variables to start this process, so on the AP test, we definitely want to show that. We can see your work. Here's where we have a problem. The reason this is calculator is because if I ask you for the antiderivative of this, please, 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 actually, let me show you when we could do this. If I gave you this expression here and I ask you for the antiderivative, then this would be 3t plus the sine of 2t. And then remember how we would divide by this coefficient? That only works if it's of this form. And that only will work if your exponent for the t is a 1. The antiderivative of this is not 3t plus the sine of t squared divided by 2t. That is not the antiderivative. I promise if you take the derivative of this, there is no chance that you're going to get cosine of t squared. In fact, we don't know how to take the antiderivative of this. All right? That's why this is a calculator question. So the way you're going to approach letter A and be able to do this tomorrow, there's another one on the next page that I'm going to leave you to do, and I'll give you the answer. The way we're going to do this, what we know is at the time of 2, our x position was, and this was given to us at the top of the page, it was 1. What we want to know is at the time of 4, what is our new x position? If this had an antiderivative, we would do it like we've done 3 or 4 times already today. Antiderivative, find your c, do the substitution, and then plug in 4. We can't do that. So the way we're going to be doing this, and we have done these before in chapter 7, we're going to take our, we wrote down this little expression, our initial position, and we're going to add the change in our position. So we know our initial position is 1. All right, that was given to us right here. The way I can figure out my change in position from 0 to 2 is by integrating, not 0 to 2, but from 2 to 4, is by integrating x primed of t. If I integrate x prime, it'll give me the change in x over that interval. So that is the expression 3 plus the cosine of t squared dt. Then you throw this into your calculator. So I know I start with the position of 1. If I now integrate x prime, that'll give me the rate of change of x, or the amount of change in x. So if I now do 1 plus, actually, let me not put the 1 in, so we know. We're going to do math 9. We're going to integrate from 2 to 4. The cosine, no, what was it? 3 plus cosine of t squared? Shoot, I'm panicking. 3 plus. Sorry, see the time click down and I'm not handling the pressure well. Let's see here. X. That's the accumulated change in our position. So 6.133, if we round that, 6.133. That's how much our position changed over 2 to 4. So my x position would be 7, the initial 1, plus the change, 0.33. All right. Now, if we have time, I want to do another one of these. But if you go to the next question, look at letter D. You're going to have to do this again. So I'm going to give you this answer just to make sure you can do one of these on your own. I'm going to write this as an ordered pair. Your x position should have been 3.954. And your y position, you should get to be 4.906. But it's the same dilemma. Here's dx dt. Here is dy dt. I want to know what's the position at the time of 3. We know at the time of 2, this is our initial position. So we want to take for the, let's set one of them up. So for x, we would take the initial position of 4 plus the change in dx dt, or the integration of dx dt from 2 is where we start, to 3, which is what we're asking for. When you do that, you should get that answer. Okay. These are all pretty nice. Let me give you this answer. This was really just kind of a little quiz review more than anything. The third one, I knew we wouldn't get through it all. These are pretty straightforward. All of this you should be able to do tomorrow. So that's the answer to that one. To be able to do a basic speed question, we did a number of those yesterday. You should get 2.275. And then letter C, you should get 1.458. That's a total distance, total speed, equation of line, stuff we've definitely done a number of in our notes. Be able to do all of that tomorrow. So let's do a little review. I would say the previous question, if you want to try it, feel free. Some of these are a little trickier, though. Outside of C is nice, but B and D are a little tricky. All right. Yeah, that's all I got. Quiz tomorrow. Yeah, I'll pop in at 9:30. If you have any questions at 9:30, I'll hop onto our link, hop in there, and I can take care of anything that you're not squared away on, okay? All right, right on time. All right, we'll see you guys. Have a good night. Bye, Shelby. Bye, Aaron. See you guys. Have a good day.